Structural dependency describe how pieces of data rely on one another within a schema, an application, or across systems. At a basic level, a dependency says that one value or structure is determined by or contingent on another. Understanding these relationships is essential because they govern correctness, maintenance, and change risk in any data system. Start with a simple example, an orders system. An order row depends on a customer row for identity and billing attributes. An order line depends on a product row for price and description. These are structural dependencies. The meaning and validity of one record depend on the existence and state of other records. Structural dependencies appear in many forms. Functional dependencies assert that a set of attributes uniquely determines another attribute. For example, a product SKU determines a product name and category. Referential dependencies, implemented as foreign keys, require that a reference points to an existing record in another table. Derived dependencies arise when a value is computed from other values, such as a line total derived from quantity multiplied by unit price. Transitive dependencies occur when A determines B and B determines C, making A indirectly determine C. These are important when reasoning about normalization and update effects. Why do dependencies matter? First, they define integrity constraints. If dependencies are violated, data becomes inconsistent or meaningless. Second, they influence schema design. Recognizing natural dependencies helps decide whether to normalize or denormalize, where to place keys, and when to capture derived values. Third, dependencies shape operational concerns. Update ordering, transaction boundaries, and the scope of migrations or refactors. Dependencies also create coupling. When many objects depend on a single table or service, changes to that central component propagate risk widely. This is why dependency analysis is a core activity before any schema change or software release. It reveals the blast radius of change. How do dependencies affect modeling choices? Normalization aims to express dependencies explicitly by factoring repeated information into separate relations and enforcing keys. When functional dependencies are properly represented, updates are localized and duplication is minimized, which reduces the chance of inconsistent copies. However, normalization often increases the number of joins required at query time, which can affect read performance. Denormalization instead duplicates data to optimize reads, but it introduces derivative dependencies that require additional logic to keep duplicates consistent. Detecting and documenting dependencies is a practical necessity. Start with declarative constraints. Foreign keys, unique constraints, and check constraints encode many dependencies directly into the database. Next, capture derived dependencies in code or database logic. Computed columns, triggers, and materialized views should be documented as explicit dependency edges. Schema registries and data catalogs that include dependency metadata enable teams to navigate the graph of relationships and run impact analyses before making changes. In distributed systems, dependencies extend beyond schema to service contracts and message formats. An event emitted by service A may be consumed by dozens of downstream services. That event's schema and semantics are a form of dependency. Consumers depend on the producer's representation remaining stable or following a coordinated evolution plan. Versioning, compatibility guarantees, and contract testing are tools to manage these cross-service dependencies. Testing and monitoring help manage dependencies in practice. Unit and integration tests should assert that dependencies hold. Foreign keys resolve, invariants are preserved, and derived values match their sources. Contract tests and schema compatibility checks detect breaking changes in APIs and event schemas. Runtime monitoring, for example, validation error rates, referential integrity violations, and reconciliation job failures, provides early signals that dependencies are breaking in production. Change management is where many dependency-related failures occur. Schema migrations that remove columns, tighten constraints, or rename keys require careful sequencing, add new fields, backfill values, switch producers, then remove old artifacts. Safe migrations treat dependency changes as multi-step operations with visibility and rollback mechanisms. Feature flags, phased rollouts, and canary deployments reduce the risk that a change will propagate inconsistently through dependent systems. There are also performance implications. Hot dependency targets, such as a lookup table used by many queries, can become bottlenecks under load. Indexing, caching, and materialized views are common strategies to mitigate read pressure, but each introduces trade-offs in freshness and complexity. Caching introduces temporal dependencies. Cached values may diverge from authoritative sources until invalidation occurs. Governance and documentation convert implicit dependencies into explicit organizational knowledge. A dependency graph that includes owners, SLAs, and contact points speeds incident response and clarifies who must be involved in changes. Document the intent behind dependencies. Why a denormalized column exists, what business rule a foreign key enforces, and which derived fields are considered canonical versus transient. Finally, some practical rules of thumb. Prefer explicit, enforceable declarations of critical dependencies over ad hoc conventions. Treat derived values as derived. Prefer computing them when needed, or maintain robust mechanisms to keep materialized derivatives correct. Always perform dependency impact analysis before removing or changing a field or service contract. Automate the detection of schema drift and failed reconciliations, so humans only intervene when rules cannot resolve ambiguity. Structural dependencies are the connective tissue of data systems. They enable expressive modeling but introduce coupling and change risk. By making dependencies explicit, documenting their intent, testing their invariants, and managing change deliberately, teams can preserve integrity while allowing systems to evolve. When you next approach a schema change, a migration, or an integration, map the dependencies first. That map is the most reliable tool you have for predicting consequences, planning safe changes, and keeping your data meaningful and trustworthy.